Welcome to this session. We're going to be dealing with the CO2 high voltage power supply today. We're going to do a bit of a dig deep into it because a few sessions ago I discovered it wasn't quite as responsive as I thought and hoped it would be. I've been trying to do high speed dotting, photo engraving with it, and I've always suffered with a problem that it's limited to about 200 millimeters a second speed. If I've got 254 ppi, that means I'm getting 10 pixels per millimeter. And if I'm running at 200 millimeters per second, that means I'm trying to produce 2000 dots per second. Now that sounds quite a lot, but it's not that much. Really want to go a lot faster, because after I did my first test, I managed to get some more power supplies supplied by Cloudray, different power supplies, to see whether or not there's any difference in the performance between HV power supplies. Maybe some are better than the others. Now, from all the information that I've researched and found out about these high voltage power supplies, it seems that the design is pretty ancient, maybe 40 or more years old. I'm not sure that it's ever been redesigned. I'm sure the old design still exists, and who knows, maybe there's a difference between this power supply and the two that have been supplied by Cloudray for me to test. We'll find out. If you haven't watched the earlier session on power supplies, then I'll just bring you up to speed on what my methodology is and what I'm doing. At the rear of the machine here, any current that passes through the tube has got to get back to the power supply, and it gets back to the power supply through this ground line. So what I'm doing, I'm measuring the current flow in this line. So I've put a 229 ohm resistance in there, and I'm measuring the voltage drop across that resistance, and it's going back into my oscilloscope. So I'm running this at 80 watts, 22 milliamps, and those 22 milliamps flowing back to the power supply through my resistor will create a voltage difference of 5. So when I look at my oscilloscope readings, 5 volts equals 80 watts or 22 milliamps. That's just to give you an idea of the scaling of what we're going to see. The data I'm measuring is with my very simple little oscilloscope here. It's a USB oscilloscope that plugs into the PC, and I'm going to use the screen as a monitor. Anybody familiar with my channel will know what this is. This is my 254 ppi test pattern. These pixels here are 0.1 with 0.1 gaps, 0.1 white pixels, 0.1 black pixels. These are 0.1 pixels, and here we've got something like a 3 pixel gap between them. Then we've got random dashes along the top line. So I'm going to be looking at all 3 lines of that signal to see what sort of response time I'm getting. Do I see a nice clean plus, minus, plus, minus, plus, minus on these signals as I go across here? Is there a recovery time that's needed? In other words, if I do this and this and this, I've got a much bigger gap in between for the voltage to recover or drop down. And then I've got all this random stuff across the top here. So we've got a whole range of signal potential here that we can look at to assess the response time of this power supply. Okay, so let's run. And there we are. We've collected our nice 3 sets of data. The dashes, the middle line, and the bottom line. So we'll go and have a look at those, and because what these are done at 100 millimeters a second and 15% power. Now 15% power on this machine is operating in something called the pre-ionization zone, which is a strange situation that exists with all glass tubes. When you switch the power on, they do not immediately fly into life. There is some uncertainty in the tube itself, and there's also some further uncertainty in the electronics in there, which is busy trying to control this uncertainty. It's like taming a bucking bronco. Initially, it's totally out of control. But hang on, we shall see that when we start looking at those signals a bit more. But before we do that, I just want to take you around the back of the machine, and I want to show you what this pre-ionization looks like. Now I want you to watch very carefully just here, and you'll see the very, very faint pink glow. The beam hasn't properly established itself. It's constant, but it's constantly out of control.
And you'll see that if you watch this, you'll see that the beam is fluttering, the intensity is varying. You'll see that from the pattern in the beam. So this is a very unstable beam. Can you see, how the centre of the beam is a bit fluttery? Okay, that's what a 15% unstable beam looks like, and that's pre-ionization. I'll now put that up to something like about 25%, and we should be out of the pre-ionization zone at 25%. Although it's not the strongest beam in the world, you'll see that it's pretty steady now. Nice and stable. There's none of that flutteriness about the beam. When I run it at 99%, you look at the brightness, the intensity of the beam now. Now you can hear that crackling. That's not the tube here. Let me show you what it is. I have no lens or lens tube in here. What we're doing is we're just bouncing the 80-watt beam off that mirror down into a cup with some water in the bottom. And when I press the pulse button, that's what the energy is doing. It's converting that water into steam. So this is the safe way that I'm going to be using this machine for testing. We're not burning anything, we're just absorbing the energy into water. Okay, let's zoom in on these signals. So here we're looking at those single pixels, which I think is pretty obvious from the pattern on the screen there. So we've got these strange spikes in here caused by that uncertainty, that bucking bronco. The electronics in here is trying to control what the tube is doing, but it's not doing it very well, as you can see. That's because we're using this at 15%. This signal in the background here is the PWM signal. Now the PWM signal is not like the PWM signal on a diode laser or an RF laser. In this case, this PWM signal is always 20 kilohertz. So this is a fixed PWM signal, but we're using this fixed PWM signal to encode the amount of current that we want to allow to pass through the tube. Basically, we're controlling the tube power with current flow. So we've got 15% on and 85% off. So if I change the power to 50%, we shall find that this becomes 50% high, 50% low, 50% high, 50% low. And we can also see that we've got 20 kilohertz speed. So we've got a marker of time along here as well. So every one of these divisions here is 50 microseconds. You'll see we've got something here which is looks very much like a decay signal into a capacitor or something. So remember, the tops of these blue are roughly 5 volts, and that's where the red line should top out. Because my system has been designed with this resistance to make sure that the red line is along there for 100% power. 80 watts, 22 milliamps. So that means I've got substantially more than 22 milliamps passing through this resistor to create this voltage here, which is nearly twice as much as 5 volts, 10 volts. So does that mean to say I've got 160 watts passing through here for a very, very, very short period of time? It potentially does mean that, because what's happening inside the tube is directly related to the current flow, and the current flow passing through my resistance tells me that it's high, a lot higher than 22 milliamps for a very, very short instantaneous period. So let's just move back along the trace. We take a look at this and we see that this is not quite the same duration as this. This one looks longer than that one. So there's some inconsistency here. I know that this pre-ionization mode for the machine is a very powerful mode. I use it all the time for paper cutting because of these very high spikes. They seem to pierce through the paper incredibly quickly without burning it, and I get a lovely clean cut. It's great for cardboard. It's also great for glass engraving, and here we can see why. We've got these very short duration high spikes of energy. So let's just go back and see what happens when we move into the dashes. But that dash never got out of bucking bronco mode. It was out of control the whole time. Here we've got 1, 2, 3, 4, 5, 6, and here we've got 1, 2, 3, 4, maybe 5, and here we've got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 250 to 350 microseconds just in the space of those few pulses. So it's not a consistent pattern. Okay, you can immediately see the ratio has changed to 50% high, 50% low, because I've asked for 50% power. Let's go and take a look at our single dots. You see, there's not been enough time. We've got a nice high spike initially, but we haven't got a repetitive spike. We've got some strange patterns that are taking place here, which are inconsistent as well for every pixel. But again, we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5-ish, 1, 2, and then it goes bonkers. 1, 2, 3, 4, 5, 1, 2, 3, 4. Yeah, so 4 or 5 is still this response time, but it's not as repetitive when we've only got one single pixel. So we've got one black pixel, one white pixel. But look at the size of these spikes at the beginning of every pixel. You know, we're getting a serious hit for every pixel, which is why this system works in pre-ionization, because we're getting a huge amount of power to help us produce a dot. Let's put the power up to 99% and see what happens. So there's those single pixels again. Huge spike, and we've got more energy lasting longer with our 99% power. We've still got some off, but we've got a lot of energy taking place in that single pixel. Does the pattern change when we move to a bigger spacing between the pixels? Even though we're running at 90% power, where there is no pre-ionization, the beam is still not established here after, what, 520.1 of a second. So let's take a look at the dashes. You see, every time we switch on, we've got our pre-ionization, our bucking bronco. Look, this lovely little pattern here is very typical of a servo control system coming into control. So eventually, we managed to tame the bucking bronco after, I don't know, looks like at least 100 milliseconds. And then we've got our 100% power. Remember what 100% power should be? Roughly 5 volts. Well, here it is. The blue is 5 volts and the red is 5 volts. So what I'm saying is we've got 22 milliamps flowing at this point in time, because that's what we calculated it would be. 22 milliamps, 229 ohms. And so there we are. We can see that we've got our 22 milliamps flowing there. But here, look, we've got substantially more than 22 milliamps flowing there. And that happens every time we switch the beam on. And this is one of the reasons why I personally believe that a tube dies. You're not supposed to run it at more than 22 milliamps consistently, but every time you turn the beam on, you are hitting it with substantially more than 22 milliamps. So there is a degradation of the CO2 because of this. So that's why these tubes do not last forever. You are gradually using up the ink in your cartridge effectively. There are things inside the tube, like if you look at your tube, you'll probably find it's got a very slight pink hue to the inner tube. Well, the manufacturer has coated that with a very, very thin layer of gold, which is a catalyst which prolongs the life of the tube, but it doesn't make it last forever. Right, so that's what happens when we just change the power. Now, what we're going to do is we're now going to leave that the same power, 100%, but remember, I'm running this now at 100 millimeters a second. So there's our single pixels, so that you get a picture of what they're roughly like and the spacing of these. You can see these are fairly close together. Visualize that, because I'm now going to run at 4 times faster. So, running 4 times faster, look what's happened. We've got our high spike, so we've still got an initial spike. Then we've got this strange thing here which never gets down to 0 before it has a go at doing a second spike. This is our black pixel, and this is our white pixel. Black, white, we've got no white hardly, because this thing has not had a chance to settle down at this point and give us the same length of black and white pixel. So you can't run fast with this power supply. So I've found a natural limitation of around about 200 millimeters a second. So let's put it back to 200 millimeters a second and see what effect that has. Well, you see at 200 millimeters a second, we can begin to see nearly, not perfectly, but nearly a black pixel and a white pixel, a black pixel and a white pixel. The white pixel is a little bit on the short side, but then again, the power is dropping off quite quickly, so it might not do too much damage here. Okay, so there's just an idea of what this power supply is doing for me. Okay, now let's take a look at this new power supply. I will continually remind you that this blue line top edge here represents 5 volts, and 5 volts on the red signal represents 80 watts, 22 milliamps, the maximum for the tube. And this is 20. So who knows what actual wattage is going through the tube at that point in time. There's a good uniform pattern here. There's consistency with this power supply that wasn't there with the previous one. Now I've taken a picture with my camera of the existing power supply that's fitted to this machine, and as I might have mentioned earlier, it's an MYJG 80. I've done a bit of a bodge job and temporarily hooked this power supply into my machine. Quite a big power supply. It's 100 watts opposed to 80 watts. As you can see, it's a completely different model. It's a T100. So let's go and look at its performance in a little bit more detail. Let's look at the single dots, and they seem to be quite a lot more uniform. So let's zoom in on some of those and see what's going on. And look at that. We have got approximately, it's not perfect, but it's a lot better than the previous unit. We've got a nice single spike, and we've got roughly half and half. So we really are burning a dot, giving it a really big smack at the beginning of each pixel. But we've got this same characteristic, which is 250 microseconds decay time. But it's pretty consistent, and that's the good news about using this for photo engraving. Consistency is the one thing that you want. Now these are the long dashes. It's a bit more difficult to see them. 2, 3, maybe 4 pixels, then a gap, and then we're looking for some fairly long dashes, I believe. But bear in mind, this is 18%, where we're in the pre-ionization zone, and we're getting this very uncertain. So we've got this degree of uncertainty here as we're producing our pixels, but there's some sort of outer control still. This is really a bucking donkey rather than a bucking bronco. So if we put the power up to something like, say, 25%, and this is the bit that really interests me at 400 millimeters a second, the wonderful uniformity of these black, white, black, white, black, white pixels. They're almost perfect in their repetition. And let's see what happens when we change the power to 50% now. It hasn't made a great deal of change to the uniformity or the pattern of these pixels, except you'll notice that the decay rate has slowed down quite a lot, so we're not getting very much white. We're getting mainly black pixels, which means they're nearly going to touch each other. The amount of white is probably 20%, so we're doing a huge amount more burning if we were to run at 50%. And we won't have the black-white ratio that we're looking for. So if we go back to the dashes, we should find the dashes are now sitting somewhere. The red line is sitting somewhere halfway up this blue pattern. So the power is settling out on the dashes. That was the beginning of the dash, and then it bounced around a bit, and then it settled out to roughly 50% power. 50% power-ish, 50% power-ish again. So the long dashes did get a chance to settle out, but having said that, the first dash or two were a bit messy, to say the least. So let's put this up to 100%, and then we should find in these dashes this red line sits up almost on top here. Settles down to roughly 22 milliamps, 100%, as you can see. It's got this bounce curve here, which is very characteristic of a servo system, an electronic servo that's trying to grab hold of the reins of this bucking donkey. Here, look, oh, it hasn't quite made it. Look, it's getting really seriously out of control here. Yeah, it doesn't like running at 100%, does it? It doesn't settle down at all. I mean, it does eventually get to 100%, 22 milliamps, 80 watts. You may well get effectively pulses in these dashers because you've got these pulse, pulse, pulse. Let's see what happens when we get to my single dots. Well, I think you can see here, although we've stuck with this fairly, not completely uniform now, it's going out a little bit now. At around about 15%, we got quite a nice curve with the ratio roughly 1:1 on my single pixels, and that's what I'm looking for photo engraving. And this is at 400 millimeters a second, remember. I've never done photo engraving on this machine at 400 millimeters a second. It starts to get blurry, starts to get fuzzy, starts to get burnt out. You get all sorts of problems when I start going over 200 millimeters a second with the existing MYJG power supply. So this looks to be a much better performer. So let's test it with a real picture and see what happens. Well, there is no better way of testing this power supply than to try some demanding photo engraving with it. This is a picture that I've previously only been able to run at 200 millimeters a second. I'm now doing it at 400 millimeters a second. The control of power with this power supply is substantially better and cleaner than what I've got with the original MYJG power supply. Now we're going to test this power supply with a little bit of a demanding test. This is Grayscale. On my early tests were not very good at all. It was very, very sluggish at responding to changes of power. Every single pixel has got a different power. It has to go down instantly and up instantly for every single pixel to find a different power, to burn each of these shades of grey a different power. Now for this test I've got it set to 10% for minimum and 90% for maximum. We should see the coding in the background on the PWM signal, which will tell us exactly when the signal changes from one power to another. And then we can see what the red signal does, how quickly that responds. I will point out there is no white in this picture, because if you remember from my earlier work, white is a very bad number for the laser. So 255 is actually switching the laser off. So we have killed any white 255 in this image, and the maximum we've got here is white 254, which is not white and won't turn the machine off. So this is a nice, what I call a clean grayscale image. We're scanning this at 200 millimeters a second. There's one scan. There's the dead area between the scans. There's another scan and the dead area between the scans. Any one of these is a scan across the rows. So let's have a look to see what grayscale is doing. This is probably the white or grey at the edge of the picture, where we're running at 10%. And remember what 10% is? It's in the pre-ionization zone. So we get out of the 10% region as we move across the picture and we get to slightly darker greys. Okay, now bear in mind this could go up to as high as 90% power for black and 10% power for white, which is low. So here we've got maybe about 40% high, 60% low. And then all of a sudden just here, it changes to like maybe 30% high and 70% low. Look, we've got a definite change here. So how long did it take for this change to happen? Let's take a look at what we're supposed to be seeing here. The image is 200 pixels per inch. So that means I'm going to finish up with 0.1 pixels and 10 pixels equals 1 millimeter. And if I'm running at 200 millimeters a second, that's what 1 millimeter is, 10 pixels. Therefore, I'm going to produce 2000 pixels per second. If I take a second to divide it by 2000, I'm expecting a pixel to take 500 microseconds. And the 20 kilohertz signal that's in the background is actually giving me a 50 microsecond scale. So 1 pixel should be 10 pulses. This one requires maybe 40% and this one requires maybe 20%. And so we've got an instant change here between these two signals. So how long did it take for the red signal to respond to this change? And the answer is it never does. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it starts to go on to something else. Just here, look, we've got a further change happening just here. So we've got a further reduction. So we can clearly see here when the pixels are changing their power. We're getting no instant steps. So this is not responding very well, even to very small changes of pixel power. So we started off in the pre-ionization zone. I'll tell you what I'm going to do. I'm going to remove the pre-ionization zone from this equation. And we're going to set the power to something like maybe 25% to 100%. So we stay completely away from this pre-ionization zone, because when we ask for 10% white-ish, we're getting this crap here. So we set that to 3095, 200 millimeters a second. We've got output direct, which is grayscale, and we're running at 254 ppi. This pre-ionization here is probably at the beginning of each scan, because remember, at the end of a scan the tube switches off. So every time it switches back on again, we're going to get the pre-ionization, but we're not going to get the pre-ionization during the actual cycle itself. So you see the power in the tube gradually changing here. We're now 50-50, and we're at about 50% power. So the power here is about right. So here we can see our classic problem. So we've got 95% power here, but look, we're not at 5 volts. This red line should be here. And then all of a sudden it decides it's going to drop down to, say, maybe 70% demand. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pixels at 70% demand. We certainly haven't dropped down by 30% or 20%. So look, at this point we've changed from, say, 70-30 down to maybe 45-55. So we've got another huge drop here. What does this line do? I'll think about it. So we now try my grey dithered pixel engraving. This was a concept that I developed to try and emulate the rapid response time of the RF system on a glass tube machine. If you don't switch the tube off, then it should technically respond instantly, because there's no reason for the current not to change instantly, except something in the circuitry seems to be slowing the response time down. So there's my dithered rows. The black dots are 0, and the white in the background and everywhere else is 254. So there's no reason for that to switch off during the cycle. So I'm now going to set the speeds up again at 200, and we're going to set output direct to on, so I've got grayscale working, and we're going to set the grayscale again 3090. All right, so we won't go into the pre-ionization zone. We'll stay away from that because that just confuses the issue. We're looking at the response speed to switch between 30 and 90. Now we can see pixels very clearly on there. Every time we finish a scan, we turn the tube off. So therefore, at the beginning of a scan line, we're going to have this uncertainty as we switch on. And then we start moving into pixels. Now, at the moment, we haven't hit any pixels. So the tube is now waiting to do something. Right, now we've hit the first pixel. And what you've got to remember is we've got two values that we're looking at here, 30% and 90%. So this represents 90% and this represents 30%. So when you see dark at the top, it's black pixel, and when you see dark at the bottom, it's a white pixel. So this has taken time to get up towards black. It should be up at 90%, which is nearly there. So it eventually made it. But look, remember, we need 10 of these for a pixel. So it's taken probably 1, 2, 3, 4, 5 pixels before it decided to get to 90%. Our more solid line at the bottom indicates that we've got a white pixel. And look, it's taken, what, if I use my thumb as a guide, 1, 2, 3, 4. It's taken 4 or 5 pixels again to get down from black to white. And then we've got a nice set of white pixels, and it's sitting there nicely at 30%. And then all of a sudden we get a demand for a black pixel, and that is 10, so that's one black pixel. And it didn't get a chance to get to 90% before it got a demand for a white pixel. So it said, fine, okay, not going to bother, I'll go back to white. This is the best way that I've found to establish how well this power supply responds. So I think we've seen enough on this power supply. This is no better than the MYJG for, if you like, grayscale engraving. That would also apply to 3D engraving, which is effectively this. Well, here's the other power supply. It's a Model Z80, which is an 80-watt power supply with its own display. This one matches the display on my machine, but look at the size of this unit. This unit would never go in my machine. This is a non-starter, even though it will allow me to run my photo engraving at twice the speed. This one probably will go in this machine if it works substantially better. But it's got to work substantially better for me to want to have to change it from something that's working very well anyway. If all these power supplies have got exactly the same response time, there is no point in me changing that just for the benefit of a little bit of extra speed for photo engraving. So all I've done with my existing power supply is pull the power plug out and pull the signal plug out and put some extension cables on them. High voltage connected, so everything's okay and ready to run. That looks marginally better than what we've seen before, but only marginally. This dark line at the top here, as we close it in, indicates that we've got the 65% power requirement. And then when we get to here, we've got the 30% power requirement, 65 and 30. They're the only two numbers that we should ever see on this display. When we've got 65% power, we want this sitting at the top here, roughly 5 volts or 22 milliamps, full output. And then when we drop to 30% power, which is here, we want this red line to drop down to somewhere about there, instantly. And then up and down and up and down, so that those up and downs are in sequence with these changes that we see on here. The response time of this power supply is no different than the others. Okay, it's very, very sluggish. It just doesn't respond for a pixel. So this is going to be no better or no worse at 3D engraving or grayscale engraving. We'll now change back to my little simple dot test and we'll see what single on-off pixels look like. Now at the moment we're only using 200 millimeters a second. So we had pretty good results with the single pulses at 400 millimeters a second and 18% power. Let's go and have a look what results we get from this power supply. These are the single shots. They're not looking bad. We've got a much sharper response time here. Remember, last time it was around about 4 or 5 pulses to get down. And this is 1, 2, 3, 4, maybe 5, but then we've got 1, 2, 3, 4. So again, we've got a pretty good ratio here of black pixel to white pixel. So this looks pretty good for doing photo engraving at 18% in the pre-ionization zone, which is what these spikes are. Let's go and look at the spaced out single pixels. A little bit more messy, but you know, I would say that this curvature here is actually sharper. In other words, it's getting down quicker, but we've still got this huge 20-volt spike. Let's have a look at the dashes. Now the dashes are probably going to be exhibiting, as they are, pre-ionization all the way through each dash because we're using 18%. I'm interested in these single pixels again. Yeah, because I'm running at twice the speed now. Remember, at 200 millimeters a second was 10 of these PWM pulses. The fact that I'm now running at 400 millimeters a second means 5 pulses here equals a pixel. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's a white pixel and this is a black pixel. That's 18% there. So let's put that down to 15%. Look at that, it's even cleaner. Now, at 600, we're only going to take about 3 pulses for a pixel. 1, 2, 3. 1, 2, 3. 1, 2, 3. Yeah. So we've lost a pixel there. So it's not that consistent at that speed. But maybe if I pushed it up to 18% power now, and that's looking better. 1, 2, 3. We might have a little bit of a problem here with the white. 1, 2, 3, 4. 1, 2, 3. It's worth trying the test pattern itself to see what effect we get when we run this as a physical test now. 11.7 at 600 millimeters a second. 18% power. But I have to say that's looking pretty damn good. I mean, you can hardly see the dots. You don't want to see the dots. The only time you want to see the dots is when they work together. 11.7, 11.7, 11.7, and 11.7. Pretty pleased, pretty happy with that. Well, it's certainly hustling along at 600 millimeters a second. And from the very first results that I can see, it's looking pretty good. We have one problem. I didn't do a calibration for reverse scanning offset at 600 millimeters a second. Now I won't stop it because it's looking good. The time we shall see whether or not the reverse scanning offset is out in any serious way is when we get to the very fine hairs on the whiskers. I can see some very fine hairs just here, and they don't look too bad at all. Now I don't like to prejudge it, but I'm pretty convinced I might be trying to fit this into this machine. Well, here come some of the hairs for the whiskers. Now if they're clean and white, as they're supposed to be, then it means you don't have any serious reverse scanning offset. Because if the reverse scanning offset was there, the black pieces outside the whiskers would carry over into the whisker and make it look grey. Now the other test that's coming up very shortly will be the eye. Does it look nice and crystal clear? I mean, the eye shouldn't look dark and black, it should be quite bright. The other thing I hope you'll notice here is the lack of overscan. I've got virtually no over travel. I mean, the over travel on the end of that stroke might be 1/4 of an inch, because I've set this machine with its accelerations right on the limit. Well, I have to say I'm pretty ecstatic about that picture. Considering there was no reverse scanning offset for 600 millimeters, that is amazing. Look at the hairs in that ear there. Well, at 600 millimeters a second, this is definitely worth fitting this into this machine. This is probably the most demanding thing you can ever ask a high voltage power supply and a glass tube to do. It's not a problem with the glass tube, it's all to do with the high voltage power supply. And the fact that this has got a characteristic in the pre-ionization zone that allows me to do this is amazing. It's the control of that pre-ionization zone that's vital for doing this sort of photographic replication work. You've seen it happening in front of your eyes. This is not a trick. That photograph has not been doctored in any way at all. It's 1 pixel, 1 dot. Am I a happy boy? Of course I am. Am I going to fit this into the machine? I think I am. Am I going to use the digital ammeter? I don't think so. So without any borax treatment, this recycled card that I bought from Amazon produces a fantastic contrasting image We're using the compound lens that I designed many years ago, which is available from CloudRay. This power supply, the Model Z80, that's available from CloudRay. My initial suspicions were right. This power supply has not changed its fundamental design for the last 40 odd years. This power supply has got much better control in the pre-ionization zone than the other two, the MYJG and the T100. You may remember that earlier on I mentioned that this very high pulsing action that takes place in pre-ionization mode is very good for cutting card very cleanly and fast. And normally I do this at about 60 millimeters a second. I'm trying this at 80 millimeters a second, seeing if we can do it. Now notice how noisy and hissy the cut is. Look, this is an amazing little machine to be able to do this. Look at the speed that it's going. It seems to work very well at sort of 80 millimeters a second. So that's how good it is at cutting card as well. Thanks for your time, and I'll catch up with you in the next session.